energy, and one big auroral display has enough electrical currents to power the US for years. And a big auroral display can happen a couple of times a day. It's a lot of energy. That energy has to be coming from the magnetosphere, and we don't know what the energy source in the magnetosphere is. It's vexing. But the reason we don't know that is because there's no way to actually image the magnetic fields. So what we're going to do is there have been advances in electron accelerators, and I've been training myself to not call it an electron gun. But an electron accelerator, you can send electrons now from our satellite down the magnetic field line, make a spot, so we make an artificial aurora that we know exactly now this spot is connected to our satellite right here, and all of the auroral stuff that's going on around there, now we can relate it to what's going on further out in space. So fingers crossed. All of you taxpayers, chip in a little bit extra for NASA. These satellite missions are hugely expensive. The mission that we're proposing for will probably be a $250 million mission. Yeah?
What is the solar minimums I keep hearing about? We're going to a solar minimum. One of the phases of the sun.
So, I was talking about the electrical currents on the sun going round and around. They make a nice firm dipole kind of magnetic field, and then you get the other currents kind of mess things up, and it all becomes kind of chaotic and turbulent. And when that happens, magnetic energy gets stored in little pockets called active regions that are associated with sunspots. And they've got very strong magnetic field loops. Any space physicist, you're going to see us do this a lot. Get stored in these loops, and when you've got a lot of sunspots and a lot of solar activity, that's solar maximum. Then, for reasons that I think we broadly don't understand, but I personally certainly don't understand, the sun goes back to a more dipole kind of magnetic field again. And the sunspots go away, and that's solar minimum. And so if you just count sunspots, and people do that for a living, there is a group of people at NOAA that number every single sunspot. We have numbered every single sunspot since a guy named Carrington in 1749 or something started doing regular observations of the sun. So sunspot number is one of our longest space physics data sets. And if you remind me, I'll tell you about something else cool that Lord Carrington did. But the other thing you may have heard is our current solar cycle has the smallest sunspot number in 100 years. And solar activity is anomalously, even at the peak of solar activity that happened 4 years ago or so, it was much lower than, so the sunspot cycle takes 11 years to go from solar maximum to solar maximum. You might actually hear about a 22-year solar cycle, and that's kind of cool because when the sun creates its strong magnetic field and then it gets all turbulent and chaotic, when that new dipole, strong magnetic field forms in the opposite direction. And then that repeats again. So every 11 years you go from maximum to minimum. Every 22 years you go from this orientation to this orientation and back to this orientation. Yeah?
So we've also heard from geologists that the Earth's magnetic field is probably starting to flip itself. So if it does do this in our lifetime or any point while we're still using satellites, how is that going to affect your research, or how could that affect what's going on with the Earth-Sun interaction?
The short answer is, I don't know. The slightly longer answer is, I've actually been on panels where we debated and discussed just exactly that question, you know. Because when the Earth's magnetic field reverses, it does the same thing. It doesn't just slowly do this. Essentially, the Earth's magnetic field falls apart, it becomes chaotic, and instead of having a North Pole and a South Pole, you've got 20 poles. And all of those poles are regions where the solar wind now can have direct access to our atmosphere. And, yeah, sorry?
Just a quick question off of that. How long does that period last if these 20 poles being active?
I certainly don't know that answer.
How
Linda,
long
you're
does it last in the sun?
on the sun it lasts for a couple of years. Solar maximum, a couple of years at solar maximum. One of the reasons why we don't know as much about the Earth's flipping magnetic field is because the Earth's field is stationary for much, much longer, and then it flips relatively quickly. And from what I understand about knowing, how do we know that the Earth's magnetic field has flipped is mostly from lava flows. You have lava flows and the iron minerals in there on fairly nearly adjacent layers can have opposite directions. But we don't have a lot of information about the in-between, excuse me. So what I can say is when the Earth's magnetic field flips, it will be a challenge on the scale of climate change. It will be a huge deal.
So could we see the aurora in Ecuador?
However the Earth's magnetic field reorients, yeah, there will be aurora all over the place. There will be these solar proton events. Solar proton events are associated with solar flares. They're super energetic protons. They have access not through the auroral oval, which is like this, but right down at the top of the polar cap. They come in if there's a solar flare going on, and this is another aspect of space weather. If there's a solar flare going on and there's a solar proton event that hits the Earth, because not everything that happens on the sun hits the Earth, right? It has to be aimed in the right direction. But if a solar proton event hits the Earth, they stop flying airplane flights over the poles. Because you can get a couple of chest x-rays worth of radiation dose in an airplane if you're flying over the pole during one of those times. Yeah.
Now, did I understand you say that we're kind of at a minimum right now?
Yep.
So does that make the upcoming eclipse more interesting or less to follow up?
Oh, that's an interesting question. If I get to see this eclipse in totality, it'd be the fourth one, like the aurora, it'd be the fourth one in my life. Every eclipse is interesting. In terms of the visual picture of things, solar eclipses that happen at solar maximum are more photogenic. And the reason for that is because of these very structured loops of magnetic field, you get, it's not as homogeneous. So you get more activity here and less activity here, and over these active regions you get what are called helmet streamers, where the magnetic field goes up like this and then it converges and comes out. And when you see pictures of the solar corona, which is the upper atmosphere of the sun, it's the corona that we can see during a solar eclipse. And so the more active the sun is during a solar eclipse, the more of this structure you're going to see.
It would seem like it would probably be maybe a lot more fascinating, but maybe harder to learn because it's so chaotic. If it's a minimum, it seems like things are more stable and you might actually be able to derive more information.
Yeah, and that reminds me of two other interesting things. One is that, nope, I forgot one. The other one is one of the missions that NASA is going to be launching hopefully next year is a mission called Solar Probe. And Solar Probe is a mission that's actually going to fly into the corona of the sun. It's going to go within, I think it's 9 solar radii, which is way, way closer than Mercury is orbiting. And it'll be our first chance to actually fly through this region of the corona, which is the source of the solar wind. We can see what's called the photosphere, the visible part of the sun. We can see that pretty easily. The corona, this was the other thing I was going to say. The corona we can't normally see. And the reason we can't normally see the corona is because the sun is really bright. And the corona isn't quite as bright.
Get the cardboard box out and
So what people do is we have instruments that are called coronagraphs that, excuse me, make an artificial eclipse all the time. And so it's a telescope that's looking at the sun and has a disk that blocks out the main part of the sun so that you can actually image the corona. And I guess what is July sometime, I guess I'm giving a Frontiers in Science lecture where I'll have pictures and things, movies of the corona, and you can see these, that's why they call them coronal mass ejections. You can see these huge explosions going off into space. And so we actually have learned more about the active corona than we have the quiet corona. But I think that's going to change with Solar Probe, because the quiet corona, there's not much that we can study. We can't. We're almost like astrophysicists, right? We can't measure it directly, but Solar Probe is going to let us measure it directly, and we'll be able to see some of those processes. And I'll get back to you in a second. One of the other mysteries that we have, and one of the things Solar Probe is going to do. The corona is way less bright than the sun, but it's actually way hotter than the sun. And how does that happen? I mean, you've got this hot thing. Usually, anything that's further away, or less dense, or less bright, is less hot. But the corona is actually way, way hotter than the surface of the sun. And this has to do something to do with wave-particle interactions, instabilities, detailed plasma physics, the kind of plasma physics that people that build bombs care about. How does energy get transferred from one population to another? So that's another thing that Solar Probe is going to do.
I was curious what sorts of novel engineering challenges there are for Solar Probe as compared to one that's a lot farther away.
Well, it reminds me of an old joke, is you just fly at night, you know?
The sun never sets on that.
So you should Google Solar Probe. It's cool, and I don't know much more than what you can get off of the internet. But they've got a double carbon composite shield. There's only one instrument that peeks out from behind that shield. That's a plasma collector. But trying to, so the instruments themselves, the spacecraft, another interesting technology challenge is how the heck do you get the radio signals back? Right? Well, I mean, they leave the sun, but the sun is bright in radio as well. So the sun gives off a lot. It's a full spectrum sun. Pretty much everything from really long wavelength radio waves to gamma rays and so on.
How do they get it back?
Well, high gain antenna. It's I'll just say I don't know. They don't have solar panels. It's using a radioactive thermoelectric generator, RTG, as the power source. And so you have to have a lot of power. Do you know?
No, I haven't known.
Okay. So it's a question of power. It's a question of picking a frequency range where the sun doesn't have quite as much emission. And I'm sure there's some kind of, encoding that happens. So, if you just flash things on and off, then you could get a lot better signal to noise by coding you're receiving to the transmission. But that's a really good question. I don't know the answer. I think over here
So
first.
how do cosmic rays play into the solar or into the space weather?
So cosmic rays are interesting. There's this whole terminology that goes back to the early days of modern physics. And so, how many people have heard of beta rays? Okay. How many people know what beta rays are? So, beta rays are just electrons that, and you can go back to the whole wave-particle duality and all of this sort of thing, which is why we didn't know what they were. We didn't know about electrons. And cosmic rays are kind of the same thing. Cosmic rays are ions. Cosmic rays are interstellar ions that have been accelerated and make it in from the galaxy back into our solar system. And tying this back to space weather again, the weather is never good in space. Just right, give it up. So solar maximum, there's all this bad stuff that's happening. Solar minimum, when the magnetic field on the sun is less structured, the magnetic field in our solar system is less structured, and cosmic rays can get in easier. So we get more cosmic ray radiation during solar minimum. And the part of the radiation belt, or the part of the space weather that I work on specifically, which is the Van Allen radiation belts, are the worst halfway in between solar maximum and solar minimum. So, go figure. There's, however, if you're going to Mars, there are better times to go to Mars. And that would be solar minimum. Yeah?
What was the other cool thing you were going to tell us about Lord Carrington?
Oh, okay. So, Lord Carrington worked in the days of physics that it kind of sounds really nice because everyone was a Lord this or a Baron von something, right? And the only people that were really doing science were really rich people, which I sometimes think, that would be easy. I wouldn't have to write grants. And then I realized, but wait, I wouldn't be one of the rich people. So, Lord Carrington was, although he squandered a bunch of his family fortune, and those of you taking notes, I hope you all are. There's a book called The Sun Kings, and if this is interesting, it's a popular science book. It's called The Sun Kings, and it starts out with a history of Lord Carrington and this event that he observed. So he had a telescope. He was interested in what was going on in the sun. He, like Galileo, would train his telescope on the sun, project it onto a piece of paper, right? Did I mention don't look at the sun? Project it onto a piece of paper, and he would sketch out what does the sun look like. And so he and some other people that were working at the time were the ones that discovered the sun rotates. And they were trying to figure out what these sunspots are. People thought maybe there were clouds floating above the atmosphere of the sun, making it dark. And so he was just, he's just doing it, but he did it very systematically. Every day, a couple of times a day, same time of day, he would go and he would sketch this out. And one of those times, he was looking down at the piece of paper and there was this bright flash of light. And, well, that's interesting. And so he made a note in his log. And a couple of days later, there were aurora all over Europe. And normally you don't get aurora over the main part of Europe. There were aurora in Puerto Rico. Telegraph stations caught on fire. because there was so much electrical current being driven through the system. And that was the first time we realized that we were connected to the sun in a way that was a physical connection. That it wasn't just heat and light, but there was something happening on the sun, and it made all kinds of really bad stuff happen here. And
What was the year on that?
I think it was 1749. What's that? No, 1849. Thank you. The sunspot numbers do actually go back older than that. That's what that. But yeah, 1800s. And